Okay, so to finish off, we ended when the bell rang today. We had talked about distance and displacement. You have the definitions from the videos from the other day. We had talked about speed and the fact that the speed of an object is the distance it travels in a certain period of time. And so the equation is VAV is equal to delta D over delta T, where the deltas mean the change in. So the change in distance over the change in time. Most often in physics, the units for speed are meters per second. We also talked about the fact that this is the average velocity. We're timing someone as they run, like a full length, maybe 50 meters, maybe a half marathon, right? So we know how far they ran and we know how long it took, and we get their average speed. It's not really their instantaneous speed. At any given moment, they could be going a speed different than that, but we're averaging it over a period of time, okay? So that's speed. Then the one, and it's a scalar, okay? So then the one we were just about to get to as the bell rang was velocity. And lots of times, the unphysicsed among us at least, think of velocity, it's a vector. We think of velocity as simply speed with a direction. Okay, and that's true as long as the object isn't changing direction. Okay, because the definition for velocity is the displacement of an object in a given period of time. Okay, the displacement of an object in a given period of time. So as long as the distance and the displacement are the same, like you walking across the room, and then like 6 meters, and then walking back. So if you're walking across, your distance would be 6 meters, your displacement would be 6 meters to the right, everything is fine. But as soon as you walk back, then you're going 6 meters to the left. Now your distance is 12 meters over whatever time it took, but your displacement's going to be 0 meters over whatever time you took. So the speed and velocity are not the same when the object changes direction. In reality, an object's velocity really in lots of cases is almost meaningless as soon as the object changes direction. Think about a swimmer doing laps in the pool, right? Down and back. Well, every time they go down and back, their displacement is 0. So you can't get an accurate feel for how fast they're going because their displacement is 0. You have to look at the distance they traveled over the time it took to get a feel for how fast they're going. So as soon as an object changes direction, velocity in a way becomes meaningless, okay? Someone running the track, right? They're running, 8 loops around the track, or running a marathon where you're in back up at the starting line, and you'd be like, gee, I don't know why you're tired. Your displacement was 0, your velocity was 0. They might not be very happy with you. Okay, the equation for velocity, average velocity, is VAV equals delta D over delta T, except it's a vector, so the VAV has an arrowhead and the delta D has an arrowhead to remind us that this is displacement, this needs a direction, and the direction of the velocity will always be the same as the direction of the displacement. Again, 99 times out of 100 in physics we'll be using meters per second. If I give you a question that has both meters per second and kilometers in it, then I'd say change it to meters per second. If I give you a question which is kilometers and hours, you can leave it in kilometers per hour. But if there's a mix of units, always change it to meters per second, okay? So these two are not interchangeable, even though the unphysicsed among us would interchange them. Okay, so just make that note for yourself. They are not interchangeable. All right, and then the other term that we need to look at is acceleration. And I know that you would have heard of this too. What is acceleration? Well, it's the change in velocity of an object in a given period of time. In other words, A, and it's a vector, change in velocity, delta V with an arrowhead, over time, delta T. we usually write it as, because change in anything is always the final minus the initial. Okay, so however fast you were going initially, and then you speed up to some rate or you slow down to some rate over the time it takes you to do it. An object's acceleration can be huge in a small period of time to get, like, someone running. If they're running sprints, they need a really big acceleration so they can get from an initial velocity of 0 to their top speed in a really tiny period of time so they can win the race, right? If you're running a marathon or something, it's not as vital. But in short races, you need a strong acceleration. Now, there are actually 3 ways you can accelerate. Okay, if you're not accelerating, but like these equations, we use them in what's called uniform motion, when there's no acceleration. But there's 3 ways you can accelerate. Okay, the first way, which all of you would know, is you can speed up. Okay, the second way, which the unphysicsed among us would call deceleration, is slowing down. It's really an acceleration in the opposite direction to the motion, right? So when you step on your brakes in the car, you're accelerating just in the opposite direction you're traveling, and therefore you slow down. Okay, remember, acceleration is a change in velocity. Doesn't mean an increase, it could be a decrease. Remember, velocity is a vector, so the other way you can change velocity is by changing direction. And so, like, if you think of someone walking around the classroom, they walk this way, they walk this way, they walk this way. They're walking at exactly the same rate. They haven't changed their speed at all, but they've accelerated because they've changed their direction. We'll get into this. This will become important when we get into grade 12, circular motion, like the rides at the amusement park or at the exhibition. The planets are accelerating around the sun because they're changing direction, even though they're traveling at a constant speed. And because they're accelerating, it plays a role into the physics that's holding them there. Okay, what are the units for acceleration? Well, the units for velocity are meters per second, and that's divided by a second. Now, the seconds don't cancel because this seconds on the bottom is like seconds over 1. And maybe somewhere in your math life you maybe learned, and if not, you're going to learn it right now, that when you divide by a fraction like this, it is exactly the same thing as if you write the top number down and then take the bottom one and flip it over and multiply. So we say dividing by a fraction is the same as multiplying by its reciprocal, the flip of it. And so when you multiply by the reciprocal, meters times 1 is meters, and seconds times seconds is meters per second squared, or meters per second squared. So acceleration is measured in meters per second squared. The seconds don't cancel here, okay? So now maybe in one question in the next 2 or 3 courses you might take from me, you might see the acceleration written as kilometers per hour squared. We almost never, ever write it that way. So in that one question, it might be that way, but any other time, always switch your kilometers per hour speeds to meters per second before finding the acceleration, because in kilometers per hour squared, it really is meaningless. And when I go over some examples, after you do some questions with this equation, you'll understand. So what are the equations?